I like to tell people I was born a physicist, and I was born a long time ago in the previous millennium. I grew up in London in the austere post-war years, and I think a lot of my enthusiasm for science was childhood boredom. These were years in Britain where people didn't have cars or televisions. You very rarely went away on holiday. Toys were expensive, and yet it was a wonderful life. We made our own entertainment. There's a form of escapism, I think, involved with science. I found I only had to look up at the sky, and there was a wonderland above my head, and I could get away from the humdrum everyday existence and find a delight in thinking about unseen things and unseen forces and the universe. So my earliest childhood experiences were asking the really deep questions of existence, as I think most children do. They think about why am I here, or why do I exist, and how did the world come to exist, and what will happen to me when I die? All those sorts of things. Most people grow out of it, but I never did, and so I'm still asking those fundamental questions, and now in a more orderly way, in a professional capacity. So I grew up in London. I went to university there, to University College London. I studied physics and mathematics, and then I went on to work in the field is mainly called cosmology, which is the study of the universe on a large scale, its origin and evolution. But I became interested in the nature of life pretty early on in my career because life seemed so weird. I've never been trained in biology. The last formal instruction in biology I had, I was up to the age of 16, so that was a long while ago. But to a physicist, life looks like magic. And so I've always been deeply fascinated by what it is that makes life tick. And given that living organisms are just made of ordinary atoms and molecules, what is going on to bestow upon this collection such extraordinary properties? And that's really the heart of this new book of mine, and the heart of my lifelong request, the heart of my lifelong quest to try to understand the nature of life.
And when you were, as a cosmologist, you were interested in astrobiology and to understand how life forms in, places that are not Earth, how they may come to be. We need to understand what life is at a very fundamental level. Like how could we class a system as living, be it the smallest of molecules or self-replicating molecules, all the way up to the complex societies that we see now. And your book, Demon and the Machine, it basically puts makes among many other points that the answer to this question is rooted in information. Would you say that's correct?
Yes. Now you've touched on a number of topics there, and I might say, as we were reflecting a bit on my childhood, one of the things that I firmly believed as a child was that we're not alone in the universe, that there is life out there, and probably intelligent life. And I was passionate about what became known as SETI, the Search for Extraterrestrial Intelligence. But in the 1960s and 70s, to profess an interest in looking for intelligent aliens was tantamount to professing an interest in looking for fairies. It was considered self-evidently absurd. All the scientists, distinguished scientists who had thought about these things, were adamant that life is just a bizarre freak accident. It's just something that's happened in one corner of the universe. It's not a cosmic phenomenon at all. And it was a crackpot quest to be seeking life beyond Earth. And that was very much the entrenched view right into the late 1970s. And then, for some reason that I still find mysterious, the pendulum swung. And today, it's fashionable to say that the universe is teeming with life. But the truth is that the scientific understanding has hardly advanced at all. And you hit the nail on the head exactly with the question about how likely is it that life will emerge, because if life pops up readily in Earth-like conditions, maybe other conditions, but if it's Earth-like conditions, then the universe should indeed be teeming with it, because we know there's plenty of habitable real estate out there. We know there are billions of Earth-like planets just in our galaxy alone. But just because a planet is habitable doesn't mean it's actually inhabited, because for a planet that could host life as we know it, life has to get going there somehow. And so the question about the transition from non-life to life, what it takes for a mishmash of chemicals to become a truly living thing, that is the key. And if that is something that is built into the laws of the universe in some fundamental way, so that it's sort of almost inevitable, we can expect there to be life everywhere. But if it's just a dream run of fluky chemical reactions, well, then maybe we are alone. And the truth is, we don't know where on that spectrum, from bizarre fluke to inevitability, the truth lies. And so there's plenty of scope here for disagreement. But the theme of my book is not so much we haven't figured out what chemicals to mix with which other and for how long. It's that it's only half the story. That the stuff of life, the molecules of which we're made and the way they're put together, is really only about what we might call the hardware of life, but it ignores the thing that really makes life magical, and that is the software. It's the information content, the information processing. And so I see the heart of the debate about the transition from non-life to life is how was it possible for molecules, stupid molecules blundering around, to basically write computer code? Because the secret of life really lies with digital information processing, well, and analog information processing. I think everybody knows that DNA is a sort of digital database. The units are the so-called letters of the genetic alphabet, A, G, C, and T. So these are discrete bits of information stored in the DNA. So we often say that DNA is the rule book of life. It contains instructions for building the organism. Whereas life amounts to much, much more than that. I think everybody's familiar with that notion that at the heart of life is an information database, and that information has to be processed in some manner for anything to happen. So here we see, at the most fundamental level, the existence of information and how that information processing system came to exist in the first place, and how the genetic code, the coding assignments that translate the 4-letter alphabet of DNA into the 20-letter alphabet of proteins, so made of 20 different types of amino acids, how that coding assignment evolved initially, we absolutely don't know. So we're stuck really on the origin of the software. That's not to say the origin of the hardware is an easy thing either, but we can sort of imagine that a chemical pathway of some sort might have led to nucleic acids or amino acids, proteins, and so on. We can sort of think that getting the building blocks of life may not be too hard, but how do you get that information processing? And how do we do that without introducing some new fundamental laws? And I think we do have to introduce some new fundamental laws. Yeah. So maybe I'm getting a bit ahead of myself.
Yeah, well, we'll come to that, but it's a very exciting proposition. So I think we all have an understanding, an intuitive understanding of what information is, and we use information, the word, in our daily language all the time. But how would you define information in this context, among other contexts? Like, is there a unifying definition, perhaps?
So this is often the problem in science, that something is used informally in daily life, and then it's used in a rather precise way in science. And physicists like to be very precise about what they are, about defining their terms, usually in terms of mathematics of some sort. And the everyday use of the term information, which is very vague, nevertheless has at the heart, I think, what most people recognize, which is if you have information about something, you are less uncertain about that thing. And so, for example, just take a trivial one, if you want to get a ferry from Balmain to Circular Quay here in Sydney, if you just show up at a random time, you're going to be faced with a rather long wait because you're uncertain as to when the ferry will come, and they're every hour. But if you get the ferry timetable, that uncertainty can be reduced. It may still be a few minutes late or a few minutes early, but nevertheless, the information in the timetable reduces your uncertainty. And that general notion was formalized in the 1940s by a man called Claude Shannon. He founded what we would now call information theory as a precise discipline, a way of calculating information. And it was he who coined the term bits, the binary digits or bits, which I think everyone's familiar with that these days. And he defined it in this very simple way. If you toss a coin, for example, it may come down either heads or tails. If you don't look, you're equally uncertain about which it is. But if you take a look, oh, it's heads, that uncertainty is reduced to zero. And that represents one bit of information, one reduction in an uncertainty from the 50-50 to a certainty. And building on that, his primary interest wasn't anything to do with life. It had to do with the war effort, actually, at that time. Supposing you're trying to communicate on a battlefield across a crackly radio, or maybe down a telephone line, a noisy telephone line. How do you encode and transmit information through that channel so as to minimize ambiguity, maximize the chance that the coded information will be correctly interpreted at the other end? He worked all that out. And then it found immediate application in many areas of science. It now pervades most areas of science. So certainly it found information theory applied to biology. We're just talking about how the information encoded in DNA is transferred to these little machines are called ribosomes. They make the protein. So they take that information and they turn it into structures, the proteins that do the work in biology. So that's a communication channel from the DNA to the proteins, classic example. But retrospectively also finds very deep applications in fundamental physics. And this goes way back because the idea that information makes a difference in the world, information can have physical clout, if you like, that was foreshadowed by the work of James Clerk Maxwell in the middle of the 19th century. I should just say a few words about Maxwell. He was a giant of theoretical physics. He was the one who unified the laws of electricity and magnetism. And so now we have this whole area of science and engineering called electromagnetism. And one example of this is radio. Radio waves were predicted from that theory. Light is an electromagnetic wave, and so Maxwell discovered that from his mathematical unification of these two forces. And so he was already very established in that field, but he had made seminal contributions to the theory of heat. It was known in the 19th century that, for example, a gas confined to a box or cylinder would represented a whole lot of little particles rattling around chaotically. The temperature was the speed of those molecules. If you add heat, they move faster. And the laws of thermodynamics, as it was called, were worked out using that basic concept. And Maxwell had this weird idea. One day, in a letter to a friend, he said, well, imagine if we had a box of gas with a screen down the middle, and the screen had a little hole in it, then mostly the molecules on the left would stay on the left and those on the right would stay on the right, but occasionally a molecule would go through that little hole and it would average out. So they go sometimes slow molecules, sometimes fast, sometimes left to right, sometimes right to left. But now imagine you had a little being who became known as Maxwell's demon, who could follow the molecules and operate a shutter. So, for example, if a fast molecule was coming from the right, might open the shutter. If it was a slow molecule, keep it closed, and vice versa for the left. So eventually the fast molecules will accumulate on the left side of the box, the slower ones on the right side, and that represents a temperature difference. And any engineer could hook up a device to run an engine off that temperature difference and do useful work, like lifting a weight or something. So here we have this diminutive being who can use information about molecular motion as a source of work. So it's like information is a fuel that can run engines. You can power a machine with information only. So those people who think that information is sort of flabby, nebulous, higher order type of concept are wrong. It actually has real physical implications down at the ground of molecules. And so this Maxwell-Demon thing lay like an inconvenient truth at the heart of physics for decades and decades. And people thought, well, is this just a bit of nonsense? Is it a paradox? Can we take it seriously? But a few years ago, people began building Maxwell demons. They can actually do this now using nanotechnology. This is technology on a molecular scale, and little nano machines can be built to implement exactly, well, very closely, the concept of what Maxwell had in mind. And sure enough, information is a fuel. And you might think, well, this is an amazing breakthrough. But as usual, nature got there first, and life is full of little Maxwell demons, little molecular machines playing the margins of the laws of thermodynamics to gain advantage. So part, but only a small part, as it turns out, of the informational story of life is something that involves fundamental physics going back 1.5 centuries.
So information is this, you could say, physical quantity that is, pervasive throughout nature, but it obviously has a use, and its use is realized in some sense through computation. Now, I've heard computation discussed in a number of different places, but I've always been a little bit perplexed as to what it actually is. Like, how does something compute something, and what is the how is it so universal, and just how does it work? It's always been a bit confusing to me, because like these little molecules are engaged in computation. Our cells are engaged in computation. Everything, all of life is a big computation. But I don't really understand what that is.
Well, and I think quite rightly you don't understand it, because I think nobody does. I should say that's a relief. That you're absolutely right. The one way of thinking about the entire universe is it's like a gigantic computer, because at any given moment, the material bodies of the universe, whatever scale you want to put it on, are in a certain state, and later on they're in a different state, and so that's like input output, and you could say, well, the universe is computing its own destiny or something like that. People write eloquently about this, but the big problem, I think, with this word computation is, when is simple information processing, just churning bits around, input output, when is that actually something like a computation? Which the word computation seems to imply some sort of utility that's involved. You compute something, not so in other words, you could take a collection of dice in a box with at rest with numbers facing up, and you could write down what that is, and you could shake the box, and then you could write down the numbers that you see at the end of that process, and then there's an input and an output. Has it computed anything? Well, no, it's just turned one lot of information into another. But that's quite different if the output of the answer is a search for something. It might be a search algorithm, or we're trying to find an optimal path between two states or something, which is a computation. Now, some people have tried to get to grips with this. So David Wolpert at the Center for Institute for the Study of Complexity has written at least about the thermodynamic cost of computation, as opposed to just general information processing. And so some people are really thinking about these deep issues, but I would say we don't yet have a very clear idea of when mere bit processing amounts to something more specific like a computation.
So there is so there is a distinction between computation and information processing.
I would say there is. I'd say when we're using the word computation, it does imply that there is an additional goal, or that the information, that the pathway of information processing is constrained in some way. There's some external factor or criterion or value that we impose to dignify with the term computation. I gave the example, if you want to look for some optimal pathway, if you want to solve, I mean, there's a famous one, of course, the traveling salesman problem. If you've got 10 cities and you want to visit each of them in turn, and you want to minimize the amount of travel between them, how do you work that out? And a conventional computer will do it really by brute force. But however it's done, it's possible a quantum computer might find a shortcut. We don't know that yet. But anyway, you can certainly say, well, here's the answer, here's the output, this is the sequence of cities. And I would call that a computation, because it's not just saying, well, let's just start out with some particular route and then arbitrarily change the routing and then look at where we've got. You're actually trying to achieve something. So I think there has to be something like an end goal or a purpose or a point in the information processing to make it a computation.
Yeah. That makes some sense to me. What I gathered from your book is that a lot of, well, life itself, but a lot of these molecules are kind of, when I say molecules, I mean, these little molecular engines, or these little ratchets, as you call them. They are kind of by design built with the capacity to process information. And while there is like some goal perhaps in that processing, one could imagine many other forms of molecules that do not exist within life, but by virtue of their composition, they end up processing information in some way.
Yes, I think life is a good example. As I said earlier, that if you've got information processing with some sort of goal or global overall value or some criterion, why it's not just arbitrary processing of bits. And life would seem to fit that definition. So the computer analogy with life runs very deep, and I think it's very popular. People are familiar with the fact, we were just earlier on talking about the genetic code. Life uses coded information, which is transmitted and translated and implemented, and it's a rule book for life, a code book for life. And that means that it's a set of instructions, and instructions have to have a purpose or a function or a meaning. And all of this goes into the normal way we understand life. And what makes that baffling in physics is that we don't see meaning or purpose or anything like that in the laws of physics. We just see molecules interacting and forces and concepts like energy and entropy. These enter into physics, but when we flip to talking about life speak, biology, we very much talk in terms of goals and purposes and signals, and even these days, of course, it's very familiar to talk about gene editing. So we think of genes as really like a text that can be edited now. There's technology available to rewrite the genes. And so genes, life writes genes and it reads out genes, and we can now do this ourselves. And so it's very much the language of information and of some sort of text that is editable.
Yeah. In this discussion of information and energy, but also complexity, the word order always is used. And order is another one of these terms that I have an intuitive understanding of, though I don't quite know exactly what it is. We'd be able to point to something that has order, but particularly in instances of life where there is so much going on, but there is, like my current state is being perpetuated across time and all that. So there is some order there, but this term order is something I also struggle with at times. So how do you conceive of order, at least in this, in this discussion of life and information?
Yes, they had to be very careful, and there's a lot of confusion, and words like order and organization tend to be lumped together, and sometimes they can be, sometimes they're the opposites. So when it comes to fundamental physics, we're in much better shape, as usual. The terms are defined very carefully. And if we go right back to Maxwell's demon, thermodynamics, boxes of gas, and so on, I'll give you a very simple example that will make this clear. Imagine if we have a flask of oxygen and a flask of nitrogen, and we put these together, then wait for a bit and the oxygen and the nitrogen will intermingle until they're uniformly spread. And we know it's impossible to separate them out again, that this is an irreversible one-way process, the mixing, intermingling of the gases. But it's very clear that the original state, with the gases separated out, is more ordered than the final state, with them intermingled. And that's an example where physicists define a term called entropy, which is a measure of the disorder. And they would say that the initial state is a low entropy state and the final state is a high entropy state. And the condition of thermodynamic equilibrium, when nothing further is going to happen, is the maximum entropy state. And all this was sort of worked out a long time ago. I also like the analogy with a pack of cards. If you go, I've never done this, by the way, but apparently if you go to a shop and buy a pack of cards and open them, they'll be neatly arranged in suit and numerical order. I assume that's true. It's a part of the folklore. And then if you shuffle the cards, they'll of course be less ordered after the shuffling. And again, if you go to a magician and say, give them this shuffle pack of cards and say, shuffle it back into suit and numerical order, and they shuffle for a bit and give it back to you in that suit and numerical order, you'll know that there's a trick involved, because you'll know that it would take a stupendous amount of time to actually find the combination that would get you right back. And so that's another good example of a shuffle pack of cards is disorderly. So you can apply this on a cosmic scale. You can say, well, if the entire universe is sliding towards a state of thermodynamic equilibrium, often called the heat death of the universe, it must have started out more ordered. So the beginning of the universe must have been more ordered than it is now. And that is indeed true. It would take us a bit off topic for me to discuss that, but what we know about the very early universe, it was actually much simpler, more smooth than it is now when we look at, compare a galaxy, or the complexity of all the stars in their orbits and so on, with just a big splodge of gas, which is how it started out. Again, you'll see that the universe began in a more ordered state. It's now in a less ordered state, and in the future it'll be even less ordered than it is now. But delving into the details of that is actually very much at the forefront of physics. It involves things like quantum black holes. You have to understand those, how they fit into the picture. And I'm not going to get into it here. But basically, there's a very clear story. But when it comes to life, then it gets very murky, because now Erwin Schrödinger, which in many ways he was the person who started this whole enterprise, in 1943 gave a series of lectures in Dublin in Ireland, which was neutral in the Second World War. So Schrödinger was sheltering from the war. And he gave these lectures with the title, What is Life? And it became a very influential book. And he put his finger on it because he said that a non-living system will tend to go from order to disorder, often called the second law of thermodynamics, but life tends to create more order from order. So it's an orderly thing that makes more order. And so he saw one of the fundamental properties of life as its ability to turn order into order and not degenerate into disorder. And I think that's pretty obvious. You know, if you seal up a living organism in a box, it will die and decay into the degenerated state of disorder. And in order to keep it alive, you have to have a throughput of energy and entropy. It's got to be open to its environment. So some people have latched on to this creating order out of chaos. They think life is somehow flying in the face of the laws of thermodynamics. It's going sort of backwards. Well, it's not, because living systems are always open systems, and any order that they create, any reduction in entropy, is paid for by the chaos, if you like, that is exported into the wider environment. And the same thing with Maxwell's demon. If you get down to the level of individual molecular interactions, it looks like you're getting a free lunch. It looks like by turning information into work, you can have a perpetual motion machine. But when you look at the specific details, there's always a price to be paid. But life is very happy, of course, to go right up to that margin. Life is in the business of processing information and hugely, and it wants to do that at a very low thermodynamic cost. Otherwise, it would cook itself to death, because every time you erase information or reset an information register, you generate heat. And that's why laptops get so hot on the lap. It's because they're processing information with an entropy cost. And life, the example I love to give is if you think of the human brain, it's got the power of computational power of a megawatt supercomputer, but it doesn't expend megawatts, it expends the equivalent of a dim light bulb. So it's a dramatic example of the extraordinary energy efficiency that these little Maxwell demons in our brains, and they really are there. They're very much like Maxwell's original demon, operating, opening and closing little shutters to send nerve signals from one neuron to another. All of that shows the ability of life to maximize its efficiency and lower its thermodynamic cost. Coming back to your original question, order and disorder, is life ordered? Well, in the strict, rather limited thermodynamic sense, it is ordered, but I think it fails to capture what I regard as the true magic of life, which is this word organization. That it's not enough to say that it's ordered. After all, a crystal is ordered, but in a rather boring way. And so life occupies this intermediate position between the boring order of a crystal and the boring uniformity of say, a gas in thermodynamic equilibrium, which is certainly very complex in a way, but it's a very uninteresting type of complexity. Life sits in the middle, where it is complex organization or complex order. We can bandy these words around, but in a way that we would like to be able to define rather more precisely. And that gets me to the heart of my book, because what I've tried to do in this book is to start out with Maxwell's demon and the demon in the machine, looking at these thermodynamic aspects, the molecular efficiency and so on, but point out very quickly that life goes beyond this, that life involves not just information processing, but information management and control on a global scale. It's not just a local thing. It's not just a molecule of one place doing one little thing and saving some energy. It's the way that in living organisms, the information is integrated across many length scales and time scales, and fulfills this type of management role, which we use this term organization. It looks like organized information management, not just sort of piecemeal. It's not just a hodgepodge of little bits of information processing all glued together. There is some coherent processes going on. And that's where the definition of information needs to be widened to include that aspect of coherence and control. And you couldn't want a better example than the development of the embryo. When you think about that, of course, there's information processing going on. Genes are being read. There's networks of genes that switch each other on and off. Information flowing around those networks. And this is not just information processing for its own sake. It's coupled to chemical networks chemical gradients in order for cells to grow in one place and not another, and differentiate into different forms. So what you're seeing in the development of the embryo is a sort of choreography which is being managed by networks of information, genetic and chemical networks coupled together to bring about this organized, coherent whole on a global scale. Now, defining information that encompasses that degree of management, or really can't avoid using the term semantics, is very difficult. So I'm using the term semantics because if you ask a biologist what is a gene, it's not just n bits of information. It's a set of instructions. And what does instructions mean? Instructions only mean something if there is a system, a molecular system. In this case, it has to do with the ribosome and all the various enzymes that make that work, that has to interpret that information and implement the instructions. So the term meaning seems to go here. The information in a gene has to mean something. If it's just junk, it doesn't mean anything, and it is not biologically functional. So pinning down that notion that here is so many bits of information which are not just any old bits, but are instructions or meaningful bits, or they have semantic content. Trying to get a mathematical definition of that is really, really tough. It's an outstanding problem. I know people who work on it. They try to see if they can formalize that in some way. But at the end of the day, I think we're going to need to find new laws. I think new physics is lurking in living matter, which will have as their basis this notion of, to use a more neutral term, contextual information. Meaning, of course, is a loaded term, but context, I think, is a rather neutral one, that the information in a gene and elsewhere in biology has to be seen in the context of the organism as a whole. And this goes against hundreds of years of tradition in physics, which is that we tend to look, when we talk about cause and effect, we concentrate on local interactions, what's happening at a point. And so if you take the example of electric forces, what's going on there? Well, you can look at a particle like an electron. Does it have an electric charge or not? So it does have a charge, and that charge is, as it were, on the electron. It's locally identified. At that point, there is the charge. But if you look at a base pair in DNA and say, is that part of biological instruction, or is it just a bit of junk? Is it a mutation? What is it? You can't tell. You've got to look at the whole system. And defining laws of physics that relate the whole to the part is a really tough one. It's not unprecedented in physics, it happens in quantum mechanics, but it's unfamiliar to most physicists. And so part of the reason we can't write down the laws of life right now is because they will evolve in some way, connecting what's going on locally with the totality of the system. And that's a tough one.
Mm. So I guess one of the things you highlighted there is physics historically has been very reductive, but to understand living systems, we need to understand emergence, and that the sum of the parts is, well, the whole is greater than the sum of the parts.
Yes, I think life exemplifies this dictum that the whole is greater than the sum of the parts. It's a very powerful example, and one way of expressing it, I often do, is that no atom in my body is alive, yet I am alive. And now if you're a hard-nosed reductionist, you'll say, oh, well, that's because you're bestowing upon this thing called life a special sort of status, but actually you are nothing but a collection of atoms, and that the fact that some particular collection or arrangement of atoms you choose to call living is entirely an informal thing, but life is not a fundamental aspect of existence. It's simply one particular state or arrangement of particles alongside all of the others, and you're vesting too much significance in it. It's very hard to convince a biologist, for example, that their subject matter is of no particular value compared to any other arrangement of things. So we do think life is rather special. Maybe it's hubris, but I'm convinced that there is something special and significant about life, and it is more than the sum of its parts. So this type of nothing buttery doesn't really help. It certainly it is of no practical value to say that if you want to understand what is going on in living organisms, the physics and the chemistry and all the interesting things they do, to say, well, it's all really just atoms interacting with each other, doesn't help you at all. So the reductionist agenda, might please some philosophers to say that the world is nothing but a lot of particles or loops of string or whatever is your fundamental unit, but it's of no real value in science. And I think it's actually fundamentally wrong anyway.
I think in your book, there's a great example that you use. How would a biologist fix a radio or something along those lines? I can't remember the name. Yeah. Could you just talk on that?
Yes. So this is, when I think back through my career, you see what has happened is that physics started out, 350 years ago, and has been traditionally a very reductionist discipline that we tend to classical stuff, particle physics, that we think, well, what is matter, or what's it made of, smash it to bits, see what the components are. And the pinnacle of this quest is the discovery of the Higgs boson a few years ago. And so this follows the tradition that you'll understand something by smashing it into pieces. And that's part of the story. I'm not denigrating what those people do. I think it's wonderful. But it's only obviously one half of the story, because even if you've got all of the fundamental particles listed in a big table, it won't explain why people fall in love or how they vote in elections or anything of that sort. And so that's the other part of the story. Now, physics, I think, in the post-war years began to get away from that extreme reductionism, and there were a lot of fields like chaos theory and complexity theory and in condensed matter physics, lots of work in the opposite direction. You might think of that as emergent phenomena or synthetic phenomena, where parts come together and produce something new and exciting. And the whole field of self-organization, self-organizing systems became very big in the 70s and 80s. The physics sort of got away from it, but meanwhile, biology that was on a roll after Schrodinger's little book triggered the industrialization of molecular biology. It's now major industry. The molecular biology became very reductionistic too. And so there was a tendency to think that everything in life could be explained by looking at what was going on the molecular level. And the high watermark of that was the Human Genome Project. There was a feeling, well, all we need to do is sequence the human genome and we'll solve all the world's problems, we'll have cures for all the diseases and so on, because it'll all be there on the DNA. It was always going to be a nonsense. You just count the number of base pairs in DNA and look at the complexity of a living organism. They clearly don't match up. So there's much more going on than just at that bottom level. But that spirit of, we've got something baffling, a living cell or something, how do we explain it? Well, let's try smashing it up and seeing what's inside, and maybe figure it out. And there is this wonderful story. It's an account written by a Russian geneticist, I believe he was, who was engaged for a long while in working out a particular type of biochemical machinery. But this is a sort of spoof on how you would go about, and how many biologists do go about thinking about a complicated component in a living cell. And he uses transistor radio. I don't know how many of our young listeners even know what a transistor radio is. When I was a schoolboy, I built one of these things, or a friend of mine built it, and I helped. So we understood how you could you buy these transistors, which were little switches basically, and solder them all together and get this radio to work. So it's all wonderful. So these things would have, I don't know, 50 components or something in total. And so the story is that this Russian biologist's wife had a transistor radio that was broken and said, could he fix it? And how would a biologist go about fixing it? And so you might imagine, well, you take the back off and you'd note that there are some colored things inside. These would be the transistors. They used to be color coded, you see, and some would be red and some would be blue and some would have stripes and so on. So the first thing you might do is, well, let's remove one of those and see if it makes it better or worse, or let's swap two of them, transpose them and see if that makes a difference. You go on like that. Or what about, you fire a bullet through and does that improve it or make it worse? And, which bits seem to be vital? And that's precisely the way that biologists go about trying to understand what's going on in living organisms. But he makes the point, which is that any competent radio engineer would know immediately what to do. They'd listen to it, oh, the sound's all distorted or something, we need to replace this bit or retune that bit. And that's because the radio engineer would understand the principles of the transistor radio, the principles of radio control. We don't understand the principles of life. If you understood what makes the cell tick in terms of its overall principles and how not just the components, but how the whole lot is put together in a coherent, integrated manner. If you understood those principles, then you could fix defects. And I have this dream. I've worked quite a bit recent years in cancer research. I have this dream that we'll be able to tackle the cancer problem in that sort of way, that we'll understand that there is, we think of cancer as in terms of physical hallmarks, and there's some very familiar ones like uncontrolled proliferation and cell motility and metastasis and evading the immune system and so on. These are all physical traits. But they're also, I think, informational traits. And that's, if you like, software glitches as well as hardware glitches. And just like with computers, you can correct, if you're lucky, you can correct software glitches by downloading a patch or reinstalling a bit of software, or ultimately reinstalling the entire operating system, and then you sort of reboot and fix the problem. That we might be able to tackle diseases like cancer in the same way, instead of just annihilating the cells. Find some way of, if you understand the principles of information management and how that information is being mismanaged in cancer, that we might be able to reconfigure it and get back to the healthy one. That may be pie in the sky. It may be easier to just find a way of annihilating all those cells, but it's a sort of, I think, a more satisfactory approach to say if we can only understand the principles of the software of life in the same way as you can understand the principles of the information processing going on in a radio, you're more likely to be able to fix a problem or understand what's going on than just sort of looking at the components and hoping you'll get some clue.
Yeah, I wanted to come to this later on in the conversation, though perhaps now's the best time. From my understanding of your book, cancer could be seen as not a case of damaged cells randomly running amok, but brought about by basically something changes in the cell which brings about an ancient historical, well-organized and efficient survival response, so that the cell reverts to a primeval state that it would have back in its genetic, back long ago.
Right. This, you're quite right, and you've explained very well the ideas that I've been developing, and now it's become a big international enterprise, including people here in Sydney who are working on this. And it started for me with the realization that cancer is not limited to humans. It's found pretty much across the whole multicellular realm. And so all birds, fish, insects, plants even get cancer, even fungi, corals, you can see cancer or cancer-like phenomena in all of these things. And so anything that is that pervasive obviously has very deep evolutionary roots. And you can ask, well, when in history did multicellularity arise? And the answer is, well, more than once actually, but starting at about 1.5 billion years ago. And so this suggested to me that cancer is a sort of toolkit of genes that cells have, which date back from this very early time, and that cancer is like a reversion to a more primitive state. It may be all the way back to unicellular. In some aspects, cancer behaves like the unicellular world that predated the multicellular world. In some cases, it looks a little bit more organized. It looks like it's on the cusp between the unicellular and multicellular worlds. And this has become very much a hot topic, as I told you. So just recently, the work of David Good and Anna Trigos at the Peter Mac Cancer Research Centre in Melbourne has shown that it's not just a straight switch off the multicellular genes and switch on the unicellular genes. It's a more nuanced picture where the gene networks that regulate the unicellular activity, so it's very ancient, go back over 3 billion years, and the multicellular gene networks, which are more recently evolved in the last billion years or so, they become progressively decoupled. So it's not a straight reversion, it's really a sequence of throwbacks, if you like, of going back to an earlier stage. And I think it's well recognized in the cancer research community that cancer cells are a bit like stem cells. I should explain that stem cells have the power to create any different type of cells. So if you get a totipotent, as it's called, stem cell, it can turn into liver, lung, skin, or whatever. But when that differentiation is completed, that's supposed to be a fixed end point. And what happens in cancer is you go the other way. You get the arrow goes backwards, you get a de-differentiation, you get a reversion from these more specialized cells to less specialized, more stem-like cells. And that's a bit like going back into the past. So we've developed this theory in quite some detail, and very unusual in biology that physicists are used to making predictions. They sit down, look at their equations, and they say, go measure this or look for that, and I predict you will see A and not B. That's the great power of physics. It doesn't happen very often in biology, but it does happen here. And that's because of a subject known as phylostratigraphy. So this blossomed during the time that I've been kicking these ideas around in the last 10 years or so. And what it means, it's a frightening sounding word, what it means is doing for genes what geologists do for rock strata, that you can sort of, just as you go down through a geological sequence and see more and more ancient layers, so you can do the same. If you look at the Great Tree of Life, you look at the genome sequences as they're available now, of thousands and thousands of species, and you look for common genes. We share, I don't know, 98.5% of our genes with chimpanzees, for example. So you can do these sorts of analyses, and then you can use that to infer the date, the branch points. How far back did we branch from mushrooms or something? Pick your favorite organism. And phylostratigraphy can give you the answer. So then you can apply this to cancer genes. If you give me your favorite cancer gene, these people I collaborate with can tell you, oh, that one's 2.5 billion years old, or that one's 400 million years old, something like that. And so we can be quite precise and say that as cancer progresses, it should upregulate the older genes and downregulate the newer genes. And sure enough, this, you can test this, and it turns out that these predictions are largely correct. The one that I think is really exciting, and was just recently the subject of just last week, the subject of a paper in the journal Science by a group at the Garvan Institute here in Sydney. This is some work that we initiated a few years ago. We discovered that there's a very famous response, an atavistic response that bacteria still use. So this dates way back. And let me just take you through this. Life on Earth has been around for at least 3.5 billion years. And for most of that time, it was unicellular. Now, when life began, it had but one imperative, which is replicate, replicate, replicate. These are just single cells that were, in a sense, immortal because they could just go on splitting and splitting and making more of themselves. Multicellularity was a very different way of doing life, because in a multicellular organism, most of the cells give up on their bid for immortality. They outsource that part to the germline, the germ cells, like the eggs and the sperm. So they carry the immortality into the future generations. The rest of the cells undergo apoptosis or cell suicide when they are past their due date, surplus to requirements. Cancer is a breakdown of that contract between the so-called somatic cells, the ones in the body that don't have that immortality, and the germline. So cancer is a bid for ancient immortality. And so single cells have had a long time to learn how to combat insults to their integrity, to their proliferative ability, their ability to replicate. And one of the things that cells learned a long time ago, as we know from dating their genes, is that if they're in trouble, they can turn up their rate of mutation. So I think everybody knows cancer genomes are very highly mutated. You look at the tumor, sequence the genes, you see they're a total genomic mess. And so people tend to identify cancer with these mutations. But what we've discovered is that cancer the cells can actually tune their rate of mutation. They can deliberately turn up their own mutation rate, their self-inflicted damage. And they do this as a means of getting out of trouble. So bacteria, when they're stressed, can undergo these mutations to find other sources of food, for example. It's called stress-induced mutagenesis. And we found some years ago that the oncogenes, older than about, these are the cancer genes, older than about 900 million years, cluster, there's a subcluster around the homologs, that's the equivalent of the bacterial genes that control this stress-induced mutagenesis. So a lot of what you see in cancer with these mutations, it's not that the mutations are caused by some damaging agent like radiation, and that causes the cancer. So the cells are actually deliberately turning up their own mutation rate. So cancer is almost like a defense mechanism that cells use when they're in a bad place. So there's carcinogens or hypoxia, low oxygen. They think, well, I know what to do here, done this for 3.5 billion years, just turn up the mutation rate and look for a way out of this trouble. And they do that with chemotherapy too. They've been bombarded with toxins and they think, right, we know what to do. We just mutate out of trouble. And that's part of the difficulty of tackling cancer.
So could chemo actually exacerbate the cancer? Because
yes,
that doesn't sound good at all.
No, and I'm an advocate of getting away from the standard of care, which is maximum tolerable dose, where you sort of bring the patient to death's door in the hope of killing the cancer before you kill the patient. It's brutal, it's unpleasant, and I think it's actually counterproductive, though I must caution, and I always do, that I am a theoretical physicist. I'm not a physician, and I can't give medical advice, but I can overall say that it makes more sense to me to do the opposite, which is minimal efficacious dose, that is, if it's chemotherapy or for that matter any treatment, that try to contain the cancer. Cancer is really, it's not a single thing, it's more like an ecosystem. And as we know with ecosystems, if you stress them, you can often have unintended consequences. So you might think, oh, we've got all these weeds, let's kill the weeds, and then you find there's a super weed that just takes over. Land management, people learned a long time ago that it's better to just try to sort of contain what's going on. And I think the same would be true of cancer. You don't want to provoke this stress-induced mutagenesis, this SOS response, this very atavistic, I'm going to mutate out of trouble. You don't want to provoke that if you can avoid it. You want to keep this ecosystem balanced and live with it. And that's possible in 95% of cancers. Some cancers, of course, if they're in the brain or something like that, that's a luxury you can't afford. But most cancers, say you've got a lump, in your stomach, say, why is that a big deal? Why is that a death sentence? And the truth is, it's not on its own a death sentence. What happens is the cancer spreads around the body. It's this process called metastasis. And after that happens, then the prognosis is very poor. But if you can contain and manage, there's really no reason why you have to annihilate every last cancer cell. And I work with, in Arizona, there's the Arizona Cancer Evolution Center, or we call it ACE, Arizona Center for Evolution and Cancer. And they're involved in clinical trials where this principle is being tried. So I think it's beginning to make a bit of a difference in therapy, but it's a long way to go. And I have to say that cancer is such a politicized disease that I think a lot of people feel they have this natural fear of cancer. And if you're diagnosed with cancer, there is a tendency to think, I want it out of me. It's like an alien growing inside me. I've got to get rid of it. Do whatever you can to destroy it. And I think we have to just get to a different mindset where we think, well, actually, anybody of my age is living with a huge amount of cancer. And the body has ways of managing those cancer cells. They're in us. Probably not in someone of your age so much, but older people have got cancer cells all over them, and the body is able to manage it. And what we notice as clinical symptoms is when those natural management processes, which are things like immune surveillance and tissue regulation and so on, when they break down. So it's a myth to suppose you get rid of every cancer cell in your body. They're in there anyway. And so if we can just get around to thinking of it as a chronic disease, a bit like diabetes, it's something that you would manage and extend life expectancy and learn to live with it. I think that would be a much better outcome clinically.
Mm. Yeah, well, it's very exciting in many ways because cancer. It would be hard to find a family that hasn't been touched by, by cancer. So, yeah.
Every family is touched by cancer. And it is, of course, a terrible thing. It depends how you cut the numbers, but it looks like it's either the number one or certainly number two killer worldwide. It's not just one of these things that is restricted to affluent countries where we're living too long anyway. It's actually really bad in developing countries.
We just don't test it as much. It's harder to, like in poorer countries, like they may not have the resources to actually identify these things. Like with the coronavirus today, they may not have as many cases because they're not testing.
Yeah, but and that's true. But even if you take the identified cases, it's still huge in those countries and growing all the time. And there are lots of things we can do. I have to say, it's a bit of a digression. Other than just going easy on the treatment, we don't really spend nearly enough time with cancer prevention because a lot of the issues here are lifestyle. I think we know we shouldn't smoke or sniff asbestos or lie in the sun too much. These are obvious sort of health things, although people still do all of those things. I'm not sure about the asbestos. But obesity is a risk factor. Alcohol is a risk factor. Diet is a risk factor. So if we manage all these things, in terms of extending life expectancy, they'd be much more efficacious than hoping for the next miracle pill, because you don't get a Nobel Prize for a good healthcare message saying, eat more of this and less of that. maybe a very worthy thing to do, but you don't go down in history as the person who discovered, the cure for cancer. And so the lure of the cure, as I call it, really distorts the funding and distorts the thinking. There's a lot of very clever people scrambling to find, another pill. But in terms of the so-called breakthrough that we keep reading about every week, there's a breakthrough in cancer. What you're really talking about is often rather modest, and it might be that a particularly nasty type of cancer, pancreatic cancer or something, life expectancy without treatment might be 6 months, but company A has produced a pill that extends that to 9 months. And then company B produces a pill that extends it to 10 months, and this is touted as B's breakthrough. But we're measuring life prolongation in terms of weeks, if not months. And this is very different from the image we will have of a pill that will make it go away totally, or maybe go away for 40 years or something. Such a thing is not impossible, and there are some examples, some specific cancers where this is in fact the case. But generally speaking, across the board, most of the progress, the most dramatic progress, I would say, made against cancer in the last, say, 40 years, is reduction in smoking, at least among males. And you really see that in the data now, and the lung cancer data is coming down quite dramatically. So that's a lot of progress. And some other stomach cancer has come down. And then the cancers you can screen for, skin cancer being the obvious example, we could bring that under much better control by having more regular checks, because you can see it, it's on the outside. So there are ways that we can improve the outcomes, but I think we've got to get away from that idea it's going to be some miracle pill.
Yeah, I liked your analogy of the weeds in the garden. If your garden's teeming with weeds, like the cure for cancer could be seen as that which just gets rid of all of them. But the trick is to not have any weeds in the first place, right?
Yes.
But that's not as sexy, right? It's not the pill that it's not the one pill that cures it all, but it's just avoid these outbreaks.
Yes.
And from the sounds of it, these outbreaks are a consequence of living. DNA damage will occur regardless of what you do. Like the very nature of living is to process information, and there's stuff going on, and there's degradation going on, and that may result in a genetic aberration which results in this. So it's a question of how to manage it.
Okay, so that's right. So cancer is not going to go away because it's built into the fundamental logic of life. It's part of what multicellularity means, and as I've indicated, we can identify the genes that are implicated, and when they're very ancient, we know they're going to be very deeply protected. And the other thing is that cancer never invents anything new. It just repurposes existing modalities. Many of these modalities or properties are important in early stage embryogenesis or in wound healing, because in both cases you want to have rapid cell proliferation. You want to have cell motility, cells moving around, and often growing in low oxygen environments, and all of these things are hallmarks of cancer. So the cancer, these oncogenes that I've been talking about, a lot of those are developmental genes that are supposed to be switched off in the adult form when they get reactivated in the tumor. So science writer in the United States, George Johnson, has described tumors as the embryo's evil twin. It's like an embryo gone wrong. A lot of the genes which are regulating it are embryonic genes. And there's others associated with wound healing. It's another sort of reconfiguration, rapid reconfiguration of things. So cancer is often described as the wound that never heals. It just goes on, doing more, trying more and more repair, more and more patch up, and doesn't ever come to an end.
Yeah, well, it's fascinating. I want to bring the conversation back to information in life, there's two things that I really want to hit on. One is top-down causality, and the other is well, yeah. Let's go with top-down causality to begin with, because that sounds, the reductionist would just balk at that and say, well, that's just impossible.
Right.
But we have observed that this could indeed be the case, and well, it could be possible that information architecture and flows can actually result in downstream or down the chain causal patterns or influences.
Yes. So you're right, and we touched on this earlier. The reductionist position is that we will answer everything by looking at the molecules down at that sort of level. And I cited the Human Genome Project as this sort of false hope that somehow we would understand everything about human beings by sequencing their genomes. We have to look at the system as a whole. An organism is, organism, organic, organization, all these terms really go together. So then the question is, if we're trying to describe, what happens, how do we unpick that causal chain? Now, in physics, you might say, well, this atom collides with that atom and it moves off over there. And it's very clear these are sort of local causes down at the atomic level, and all that's very well described. And then if you go to some higher level, like a gas, I was talking about gases in boxes, then you forget about the individual molecules, unless you're Maxwell's demon, and you just look at the overall averaged out state of affairs and so on. And these are completely different conceptual levels. A gas and an atom are separate things, and there are laws that describe both, and those are supposed to be consistent with each other, but we don't get those levels tangled together very often. But in biology, the levels do tangle together. That what goes on, a particular gene switching on, may have huge consequences for the organism as a whole, and what the organism does, its behavior, its microenvironment, could affect what is going on at the genetic level. So these different levels get mixed up. So when we talk about cause and effect, it becomes a real tangle because of these feedback loops between the higher levels and the lower levels. And I want to give you a couple of examples to make this clear, because otherwise it's just words, that I think everybody would recognize that if a particular gene gets switched on, it may have a consequence. If it's a bacterium, for example, and it upregulates a particular gene, that might enable it to move in a certain direction or metabolize a bit of food or something like that. And so clearly, the instructions in the genes can affect the behavior of the organism as a whole. But this works two ways. And there's some dramatic examples that physical forces acting on cells globally, on the cell overall, can affect gene expression. And there's a wonderful example from my university, at Arizona State University and our Institute of Biodesign. A scientist named Cheryl Nickerson sends bacteria to the space station to see how they get on in orbit. And it turns out that the genes they express in microgravity can be very different from what they express on the ground. And you might think, well, what's the point of that? Well, everybody knows we have this microbiome inside us that in addition to the cells of our own bodies, about 1 trillion bacteria and other microbes called archaea in our gut and in every organ, it turns out, and they're necessary for human well-being. If they don't like floating in space, if they're going to start behaving differently, then it could make astronauts sick. And so that's the motivation that she's working with NASA. Another wonderful example, which I talk about in the book, is the work of Michael Levin, Tufts University, and he likes to chop up worms. There are certain worms that if you chop them in half, the head grows a tail, the tail grows a head, and you have 2 worms, so children love this. You can chop them into many different bits, actually, and they remember which bit was facing forward and which bit was facing backwards. And he's discovered there's an electrical story that gives them that orientation information. And by mucking around with the electrical story, he can induce them to grow 2 heads or 2 tails. And then what he finds is that if you chop up a two-headed worm, it makes two-headed worms, and the same with two-tailed worms. You get two-tailed worms. So this so-called epigenetic information, this morphological pattern that looks like different species, they have identical DNA, but this information is being propagated from one generation to the next. And so he found that if you send the middles of chopped up worms to the space station, about 15% of them came back with two heads. So again, the gene expression seems to depend on the physical environment. You see a much simpler example, I mean these dramatic and entertaining examples, much simpler example is if you grow cells in a petri dish, that they will, if you do it carefully, they will grow until they reach the edge of the dish and then they stop. It's often called contact inhibition. When the cells get too crowded together, they stop growing. They think, oh, there's not enough space, we stop. Cancer cells switch that off, by the way, which is part of their ability to grow in this uncontrolled manner. So what you're saying is that the physical forces acting on the cells affect their gene expression. The same is true of shear stresses. People study, so part of my colleagues' work at Arizona State University is to look at if a cell is subjected to shear stress, as it might, for example, if it's a cancer cell in the bloodstream, and differential forces acting on it, it greatly changes its physical properties. It can become stiffer or can become looser, can become softer, which helps cancer squeeze through little gaps. So we see time and again that what is happening to the cell as a whole can affect the switching on of genes. So if we're talking about cause and effect here, we have to have an arrow going up from the molecules, from the genes, and coming down from the organism and its microenvironment, not just the cell itself, but what's going on around the cell. All of these things can affect what is happening. And so top-down causation really refers to the fact that the full picture has to take into account the arrows going both ways. And if we ever want to come up with, as it were, laws of life, to find some new way of describing the software management that is part of the story I'm just saying, it's going to have to include this two-way information flow.
Mm. Oh, it's fascinating. I remember when I was reading about the worms and the two heads growing, it was just mind-blowing.
Davies says that if you came from Mars and you looked at this, you'd be sure that these were two different species and would be staggered to find that they actually have identical DNA.
Yeah. One of these laws of information, perhaps that it wouldn't be a law, but something that is definitely, as we have observed, to be a driver of life is uncertainty reduction, and that the creation of order, or just the entire act of life itself, is at least in part taking in energy, processing information about the environment in order to, survive, procreate, and all of that. What are your thoughts on uncertainty and the role it really plays? I did an interview a few weeks ago with a guy called Maxwell Ramstead, who he's working on the free energy principle. Are you at all familiar with? Yeah. And I just thought it was absolutely fascinating that the urge, or that life exhibits this this drive to minimize surprise, and it seems to make a lot of sense, at least intuitively, because if that which is surprising is not always good, it could result in death or harm. But also just in my own life, and I think we all experience this, that uncertainty is the worst thing to experience. If you go to the doctor and you're getting a test for cancer, let's say, the 3 days of waiting is a lot worse than getting the news, good or bad.
Yes. Well, you're absolutely right. And again, it makes sense to try to sort of boil this down to the simplest cases. If you look at a bacterium, it's living in an uncertain and potentially dangerous world, and it's trying to optimize its chances of survival. And this can be analyzed in sort of robotic language, and people do this, and very clever people look at the information that bacteria might garner from its environment, and this might be chemical gradients or light or something, you know, that sort. And that information then will, of course, be processed, and there has to be some sort of algorithm or some way of optimizing that, so it will make, on average, the right decision. It might be turn left or turn right, or swim this way or go backwards, whatever it is. So it's a very simple little robotic type device, but it's had billions of years of evolution to refine the efficiency of this information garnering, processing, and then implementation of a response. And people measure these things, and they try to figure out exactly what is going on. Where it becomes sort of murky, but also quite interesting, is this just taking place in what is often called the epigenetic realm? In other words, is this just the information being processed, the forces acting and so on locally, or is there actually a genetic component? Is it conceivable that not only just for behavior, but that cells can re-edit their own genomes to deploy tricks that have been learned throughout history, 3.5 billion years of history? Can they change not only their epigenetic response, but their genetic response as well? But that's an open question, but I'm sort of intrigued to think that their genes have evolved to embed contingency, because the one thing, you know, if you live in an unexpected world where there can be some nasty surprises, it pays to have a few tricks up your sleeve that you may never ever need. But if in event of some emergency, you know what to do. And life has had this very long time to plan for contingencies. And these contingencies may represent parts of the genome that are, you know, mostly not deployed, but they can be if circumstances allow. And so people will analyze all this type of stuff mathematically to see how well that information processing, garnering, processing, and response is being implemented. And this is a very hot topic. So it's right at the forefront of trying to understand the crossover between, if you like, life, computing, robotics, chemistry, and information. It's very exciting. And I think if I was a young person getting into science today, I would want to be in that sort of crossover area. We don't have a name for this field. I'd love to invent a name that represents where all those disciplines are coming together, because it really is a mixture of information theory, computing, robotics, nanotechnology, physics, and chemistry, and there's some quantum stuff thrown into the mix as well. We need some sort of sexy name and a whole industry around that. But that's where the action's going to be in the next 20 or 30 years.
Yeah, it's I think we're seeing that this as a general trend in science, that there's a lot of integration going on, integration across different disciplines. I mean, you know, last century could perhaps be characterized as, at least from a scientific perspective, as the chopping up of the world into disciplines, and then those disciplines investigating specific phenomena through their own lens. But as we're beginning to, as we are realizing on an ongoing basis that the world is completely interconnected, and that there are commonalities in some disciplines, or that there are commonalities across all disciplines. Information could be, you know, one of the best examples that just information is pervasive. And I think it's just very exciting to be a scientist today, because you don't have to stay in your box. And if you actually wish to do some groundbreaking work, you want to get up, you want to make your box as large as possible in a way, and bring in tools that are being used in you know, what some would conceive as far removed disciplines.
We do need enlightened university administrations, though. And Arizona State University, where I work when it's not locked down, is a classic example of a university that prides itself in dissolving the traditional subject boundaries, and it's has this word transdisciplinarity at its core, and really does encourage. I think many universities pay lip service to, oh well, we must allow people to sort of work across subject boundaries. They don't actually do much of it, and a career path for a young person is a real problem, because what you tend to do when you start out is you're working in some little narrow field, and you want to build up a track record. You want to become known to the handful of people who work in that area, so that you can get yourself a better job, or any sort of job. In fact, it's always a struggle. And to say, well, you know, I started out looking at molecular machines, but now I'm doing you know, information theory, and the next week I might try a bit of robotics or something. I know one or two people at Arizona State University who have done this, who actually straddle those areas on a day-to-day basis. But mostly, when you're starting out, the whole career structure is against you. There are some enlightened companies or philanthropic organizations that can see the more open view, open approach is worthwhile. But this is soft money. This is not a career path in a university environment. So I think we've got a long way to go before we get away from that old-fashioned traditional way of thinking.
Do you have any advice for scientists out there, you know, looking to answer big questions?
Yes, and I use this advice all the time, because I have people working with me at ASU who are faced with exactly this. And I say, well, you're the young people, you're the future. And so what you do is really, really important. And my advice, because we're sort of stuck in ASU is very enlightened, but most universities aren't, and people will, you know, want to go on and get jobs in various research labs and universities elsewhere. What I say is have some sort of core discipline that you contribute to, and be absolutely strong and become a world leader and be completely certain, even if it's rather narrow. Pick one particular thing where people could say, well, you can't be faulted on that. And maybe that's 50% of your time. And the other 50% you can explore all this stuff. And that's what I did. I built up a reputation in an area called quantum gravity, or really the theory of quantum fields in curved space-time, and contributed lots of papers, you know, precise results, built up a track record in that area. And that stood me in good stead. But all along I was thinking, you know, what is life? And is time travel possible? You know, and all these sort of wacky things, which I can now. I've reached the age where I can indulge all of this stuff. But for a young person, you know, it's important that they don't just do all these sort of fun but fringe things. They've also got to have an absolute core of something that they can be respected for.
Yeah. Well, I'm sure that some of our listeners out there will really appreciate the information. I just feel silly saying the word information, you know, given the context of the conversation. So I guess to wrap up, how would you paint a picture? I mean, it's not really a good question, but if you were to just speak about the role information is going to play in our understanding of the world and how we relate to the world and one another, and I guess that it's vital importance, because it's something that's we've only had as a category, let's say, for what, less than a century. So this.
Yes. So there are two ways I can answer this, because I think there are two huge bits of unfinished business for any young scientists who are thinking how they could contribute. One of these we've been touching on throughout our discussion, which is that information in the Shannon sense of just mere bits, which helps explain how Maxwell-Demon works, is completely inadequate to describe the full range of phenomena going on in life, that we need something like contextual information, or information with top-down management, all those sorts of things. And There's been a few skirmishes with trying to get to grips with that, but really that's an area which is wide open for people to be able to contribute. That's one. And the other is that I really do think that information is the unifying concept that can bring physics and biology together. And I'm not alone in that. And one of the important things that needs to be done is, even within physics, there are some people who think that information is really the primitive concept. In daily life, we tend to think, well, matter is the stuff of the world, and information is a sort of higher order property that we might be instantiated in material objects, but it itself is a sort of abstract thing. But there's certainly some physicists who think exactly the other way around. They think that ultimately the entire universe is just built out of information. It'll be quantum information. It's often called qubits rather than bits, but that's a technicality. That doing science means at the most basic level, if you're doing something at an atom or an electron or something, you ask it a yes/no question and you get an answer you interrogate it. You interrogate nature. That's how you do science. You interrogate nature, you get answers, and in the most basic level, they're yes/no answers to questions. Is the spin pointing up? Is it pointing down? Something like that. And so some people want to build physics out of information. So not out of matter, not out of particles or strings or anything else, but information as the core primitive concept. And then an atom might, or so a particle like an electron, might be simply a pattern of information or an expression of information in some way. So information will be absolutely central to physics, as well as the unifying glue in physics and biology. And both of those fields are ripe for further development. So that's what I would recommend young people to look at if they really have that sort of passionate interest in getting down to the most basic aspect of what is going on in the world.
Mm. And as a last question, what are you really excited about at the moment? Because I think just from the conversation we've had, we can kind of glean what that may be. But is there anything in particular, any recent development that you find to be very exciting?
Well, there are developments in experimental science and observational science that, of course, I get very excited by, and there's always at any given time, particle physicists think that they're glimpsing evidence for another particle, and now the most recent, just a week or two ago, is there some additional type of neutrino that is we're glimpsing, and that's always very exciting, and I follow that. The other big thing on the experimental front has been the final discovery of gravitational waves, and now the use of gravitational telescopes, as they are effectively, to look at black hole mergers and things like that. So all of that stuff excites me a lot. But in my own research, which is always much more theoretical, I have been in all these areas like cancer research and nature of life and so on. But I always regard that as a hobby, and the real job is what I touched on, the theory of quantum fields in curved space. I'm just right now working on a problem with a couple of young people at ASU, which combines these two aspects of my life. In a flight of fancy, put in a research grant application in which I wanted to apply Maxwell's demon to a particular cosmological model. It's often known as de Sitter space. It's a universe that expands exponentially fast. And it's the way we think that the universe behaved in the first split second. And it has very particular quantum properties. And in particular, it has a temperature associated with it. And that temperature is manifested in the ripples in the cosmic background heat radiation. When you look at the sky, do a heat map of the sky with a satellite, you find little splodges, hot spots and cold spots. And we think that is a manifestation writ large in the sky and frozen for all time of the thermal properties of this so-called inflationary phase, this de Sitter phase in the early universe. But when you actually look at the theory of this, as I did right back in the 1970s, there's some oddities about it. It's similar to a black hole. There's an event horizon, but it's out there instead of inside. Just as Stephen Hawking showed, a black hole has a temperature, so this temperature of this de Sitter space seems to play a similar role. It seems to have an entropy as well. All of these things seem to work well, but there's some peculiarities about it as well. So I'm trying to apply the concept of Maxwell's demon. Just like the demon can can use information as a fuel, can you power a little machine from the heat of the universe on that type of universe? And would the laws of thermodynamics go through? So it's not a very technical answer, but that happens to be a thing I'm working on.